All right, let's get started. So this is practice exam 5. And if you ran across any questions like Erica did, where you're like, oh, this one is weird, we'll get to it. We'll do it. And again, your exam is technically, it's due today. So I'm only going to take about this first hour of our 2-hour broadcast to do this, and then I'll let you guys go so you'll have some time budgeted in to take the test. But let's start at the beginning here. And we're looking at Bronsted-Lowry acid. So this was one of the first things that we did in our lecture on acids and bases. We defined what makes an acid and what makes a base. So what is a Bronsted-Lowry acid? Donates protons, or the H+ ions. So it's going to be this last one here, right? Remember that protons, or proton is our word for the H+ ion, because hydrogen only has one electron and one proton. So if you take away its one electron, then all that's left is a proton. So we know the Arrhenius definition, which we used way back in chapter 5, says that it increases the concentration of H+ ions in solution, right? So this would be our Arrhenius definition of an acid, right? But this is our Bronsted-Lowry definition. What would the Bronsted-Lowry definition of a base be? In case I asked that question. It would be, accepts. The base accepts. So my acid donates, the base accepts. And you could say H+ ions or protons. Okay, excellent. Question 2. Which of the following species is most likely to act as an acid in solution? Good. Remember, our acids, in order to donate an H+, you have to have an H to donate. So for instance, PO4 3- is flat out because it doesn't even have an H. And then you look at these other species with H's and you see, they have H's, but they would never donate them, right? That's going to split up into the sodium ion and the hydroxide ion. It's not giving away his hydrogen for anything. NH3 we talked about is a base. It will accept a proton to make the NH4+ ion. It would never give one away to make an NH2- ion under the conditions that we've talked about in this class. On the CH4, again, these are covalent compounds. They're not going to give away their hydrogens. But we know that if you give away the hydrogen on H2CO3, then you get the polyatomic ion HCO3-. That's one that you've memorized. That's a thing. So that should be the one that you feel the most comfortable doing. This is from section 1 of your first worksheet on your acids and bases work. And this is from the next section of your worksheet, right? Which is the conjugate base, right? So you're going to identify one of these in the reactant is the acid, one is the base, and then one of these is the conjugate acid, and one of these is the conjugate base. And Sarah has got it right. The conjugate base is the one which, if you go backward, is going to accept the proton. That means it's a base. And going backwards, this has one more hydrogen, so that means that this is the conjugate base. It's also the thing which is comes from the acid, right? So if you look at these two, you'll see that this is the acid because it's donating the hydrogen. So what it produces is the conjugate base. Good. Good. Okay. All right. Oh, now we're into the math. Now, before you even start this test, I actually strongly recommend that you do a little bit of a brain dump. You pull out your equation sheet that you've printed out and you write out your roadmap. And I'm going to do that right now to show you how I recommend that you do that, because it's going to be your best friend in answering all of these math questions. So here's our conversions roadmap from the equation sheet. And we just said B is going to stand for bases, right? And the A is going to stand for acid. All right. We also have this fancy little thing. I recommend you do this before you even start the test, so it's just there and you could refer to it when you need it. And you don't have to kind of build it new anytime that you get to another question. All right, so from moles, we learned in chapter 9 that you can find concentration from here. And concentration of my acid, and particularly I could say concentration of A, but I'm going to say concentration of H plus because that's what the acid forms in solution, right? And OH minus here if I've got a strong base. And of course you can go both directions here if you have the volume, right? This is exam 4 stuff. So hopefully by now this feels really comfortable to you. So what's new with this particular chapter is then to say, well, if I have the H plus and the OH minus, then I can use these equations to find the pH or the POH. So I can go again, and now there's 2 arrows because there's 2 different equations. They're technically the same equation if you're like super good at the properties of logs, but I don't necessarily care that you're super great at the properties of logs. I don't mind giving you both equations. But from the H plus you can find the pH, and from the OH minus you can find the POH. And to go this direction, you're of course going to use this equation. The pH equals the minus log of the H plus. And of course here, POH equals minus log of the OH minus. And then to go backwards, if you have the pH and you want the H plus, then you're going to use this equation, H plus equals 10 to the negative pH. You guys remember this? Hopefully this isn't crazy unfamiliar to you guys. Okay. So it's just kind of a matter of putting it in and having it there ready for you when you're doing your problems is just really nice. And then of course, once you have the POH or the pH, you can find the pH or the POH, right? The other one. Using this equation here. Again, this whole set of equations is given to you on the equation sheet. It's just not given to you in the conversions roadmap. So you kind of have to put this together. pH plus POH equal to 14. That's the equation you're going to use here. And hopefully you guys will remember, this is important to note, right? That all of this coming from the moles of the acid and the concentration of the acid, this is applicable to the acid only. So this is the pH of the acid solution and the POH of the acid solution. And because this is coming from the moles of the base and the concentration of the hydroxide, this refers to the POH of the basic solution only and the pH of that basic solution only. Does that make sense? Okay. All right, now that I have taken some time to do my brain dump, as you call it, right? Everything that I've been trying to make sure that I remember for this exam. I'm going to come over here and look at these questions. So I've got an equation, lithium hydroxide reacts with HBr to make H2O plus LiBr, and it looks like it's balanced. And they're asking 0.458 liters of HBr at what concentration will react with 0.582 moles of lithium hydroxide. So I'm going to write all over this, so I'm going to move it down here. and say, okay, for this question, question 4, they gave me volume of an acid solution, right? HBr is the acid. I should probably have asked you guys that, but you guys can see that HBr is the acid in this equation, right? Okay, yeah, 0.458 liters of my acid solution. And they want to know what the concentration of that acid solution is. Hopefully you can see that when they say at what concentration, they're talking about the acid here. Okay. And they give me that I have 0.0582 moles of lithium hydroxide. So that's my moles of my base. Moles. Okay. All right. So this is a pretty short jaunt, right? This is a very simple question, relatively speaking, to what I could ask you, but it doesn't ever hurt to have and use the roadmap and just say, okay, it'll tell me, it helps tell me how to answer even these relatively easy questions. It says, look, if this is what I'm looking for, then I need to start at the furthest position, that's here. And the roadmap says I've got to use the coefficients to get to moles of the acid, and then the volume, that'll give me concentration. So this is a 2-step. But the roadmap just keeps me on track and says, here's what you need to do when you need to do it. Each of these steps is pretty easy. It's very easy to get them mixed up. All right, so we have check it out. Do you see what I did here? My most common mistake is to transpose and be off by a power of 10, right? Oh, 0.0582, that was almost a disaster. Okay, look, there we go. Okay. Doesn't ever hurt to triple check your sources when you're putting in your numbers. 0.0582 moles LiOH. And the roadmap says use the coefficients, and we already said that was balanced. All the coefficients are 1 and 1, so that's really nice. Okay. 1 mole of my HBr is going to react with 1 mole of my LiOH. Good. Excellent. You got it. And now, once I use that, I should be at moles of A, and sure enough, my moles of lithium hydroxide cancel, and I have moles of the acid. Now I'm going to use the liters to find concentration. That's units of moles per liter. So I know I've got to put that on the bottom. Perfect. You guys are prepared. 0.458 liters, my HBr solution. Okay, and moles per liter is the units of concentration, so I'm done. And I can just stop right there and plug it into my calculator and say 0.0582 times 1 divided by 1 divided by 0.458, and I get a concentration of 0.127 molarity HBr. Everybody follow what I did there? Okay. And again, you might have been able to do that without the roadmap, but if you've got the roadmap and you're using it, which you should, it never hurts, right? And it can certainly almost help. Same thing with this question. You could probably just look at your equation sheet and use the equation there, but you've got the roadmap, why not, right? What's the pH of a solution with an H plus of 5.9 times 10 to the negative third? Well, if I've got the H plus, my roadmap tells me how to find the pH. I'm just going to plug that in, right? Using this equation. So the pH equals the minus log of the H plus. So here we go. 5.9 times 10 to the negative 3. And I really sincerely hope you've all practiced doing these with your calculators. Every calculator is different. All right, so I'm going to take the minus log of that, which for this calculator says I'm going to take the log of it and then the minus of that. And that gives me a pH of 2.23. Just what Sarah got. Perfect. Any questions on that one? Okay, good. Question 6. How many moles of pure sodium hydroxide must be used to prepare a 1 liter solution that has a pH of 12.29? Again, you can use the roadmap. You can say, look, they gave me the pH of a base and they want to know the moles. So, all right, so they gave me, this is the basic section, pH of the base, and they want to know the moles of the base. So I'm just gonna follow this little chart right there and start by saying the pH of a basic solution isn't actually that useful. I need the pOH, so I'm gonna subtract 14 minus 12.29 gives me a pOH of 1.71, right? So this was 12.29. Oops. 12.29. Plug it in backwards. 1.71 is my pOH. Now to get back to my OH concentration, I'm going to take 10 raised to the negative that. Okay, 10 raised to the negative 1.71. That gives me 0.0195 moles per liter right here. And now I'm going to use the volume, which was 1 liter, to find the moles. And so let's put this 0.0195 moles NaOH in 1 liter of an NaOH solution. And I'm going to run that little guy. It was in fact a 1 liter solution. Sorry, this was solution. Okay, so my liters cancel, times 1 divided by 1. Okay, so that's the number of moles. 0.019 right here. Okay, Sarah says my math is getting muddy. Oh, good. That's why I took a copy, right? Make another one. This is actually way better than doing it on the chalkboard, because on the chalkboard or on the white erase board in class, I can't just copy and paste it so easily. That's kind of nice. Okay, but were there any questions on this one right here? Okay, we're good. All right, so let's do this one. 240 milliliters of an acid solution with a pH of 1.3 is needed to neutralize 340 milliliters of a basic solution of unknown concentration. What was the original pH of the sodium hydroxide solution? Okay, so we're going to use our roadmap, but we need one more thing. And the thing that we need is the equation, right? Yeah, because last time we were given the equation. This time we need the equation. We're definitely going to need the equation because we need to know what that mole to mole ratio is for this piece, okay? So if there's ever a reaction, make sure that you've got it written out and balanced, because there's no guarantee it's going to be a 1-to-1 ratio. So HCl plus NaOH gives me H2O plus NaCl. That's it, because the H and the Cl are plus 1 minus 1. The Na and the OH are plus 1 minus 1. It all works. Okay, so now just to orient ourselves on our roadmap, 240 mils of an HCl solution, is that the acid or the base? That's the acid, 240 milliliters. I'll put that right there. Okay, and that acid solution has a pH of 1.3, so the pH of the acid, 1.3. Okay, and 340 milliliters of the NaOH solution, that's your base, right? 340 milliliters. And we want to know what's the original pH of the base. So we're all the way over here, pH of the base. So again, we start at the furthest position here, right here. We're going to go this route, and then this way, and then this way, and then this way. I'm just going to keep going. It's a lot of steps, but you know how to do each of them, and if you've pulled out your roadmap, then it's going to just tell you each one. So the first step, to go back from the pH to the H plus of the acid, I'm going to use this equation here, right? H plus equals 10 to the negative pH. So 10 to the negative 1.3, 1.3 negative 10 raised to that gives me H plus concentration of 0.0501. Okay, everybody agree with that? Okay, moles per liter. All right, these are equations, but here I've got to do dimensional analysis. So I'm going to put this down here. This is moles of my H plus per liter of my H plus solution. Okay, and now the next step, I've got to use my volume to get to moles of my acid, right? And this is in liters and this is in milliliters. So Sarah says, I'm not going to waste time with that. It's just 0.240 liters. If you haven't got to the point in this semester yet where you can look at milliliters and instantly translate that in your mind to liters, that's fine. You can still take the step of saying that every 1 liter has 1,000 milliliters and then put your 240 milliliters up there too. We're going to put it there. This is my H plus solution. Here. Okay. All right, so my liters of my hydrogen solution cancel. And I'm left with moles of the acid, which is just where I was hoping I would be. And as you guys have noted already, it's a 1-to-1 ratio here. So we're going to put 1 mole of NaOH or OH minus for every 1 mole of my H plus. Right, both of these are strong. This is a strong acid, strong base. They dissociate completely. And my moles of H plus cancel. So now I'm at moles of my base, and now I need the volume of my base to get to my concentration, which Sarah says I'm going to just convert that to 0.340 liters, my OH minus solution. Okay, and moles per liter, that's the units for concentration, so I can stop there and just plug it in. And we have 0.0501 times 0.240 divided by 0.340, and we get a total concentration of 0.0354 molar hydroxide here. Okay. All right. So now our roadmap says, okay, I'm going to plug that into this minus log equation, and that gives me the POH. So the minus log of this, or the log of that, and the negative of that, gives me 1.45 for my POH. And my roadmap says, wait, you're not done, which is good, because a lot of students would stop right there and might accidentally select the 1.45. Right, but we have to subtract that from 14. So subtract that from 14 to get the pH. Gives me a pH of 12.54. What do you guys think? Phew, that was the hardest one. I think that's the hardest one on this whole test. In terms of just like multiple steps and working through it. But if you've got your roadmap, it's work, but I don't think it's super hard. It just takes time. Any questions on that one? Erica and Sarah are rocking this thing. Okay. Now, of course, all of these equations and the roadmap and all of this only works for when we're neutralizing an equation like this, if we're using like a strong acid or a strong base. And it doesn't work for weak acids or weak bases, because with a weak acid, we can't make the assumption that it dissociates completely. So here's a definition question, like what is a weak acid? And a weak acid is one that will only slightly disassociate, right? That it has this reversible reaction, right? So if we compare, for instance, HCl, put that in water, I get H plus and Cl minus ions, and it's pretty much 100% dissociated. Whereas if you put acetic acid, which is HCH3COO, in water, then I get the forward direction, sure, but then I also get the backwards direction, right? So I would represent that with the double arrow to say, actually, it's not complete. So I can't say that it's a 1-to-1 ratio because it depends on the K value wherever this equilibrium lies. All right, that makes sense? It would be the same for a weak base. A weak base only slightly dissociates into hydroxide ions. It's the same thing. Okay, so that's the definition of kind of the weak versus the strong. And now we're looking at a buffer solution. If I use the word buffer, then we're talking about a system with weak acids and weak bases, right? So aside from the conceptual one that we had here in question 7 or in question 8, the rest of these might be using this one equation here. This is what you have to use if you have a weak acid, a weak base, or a buffer system. That's what they want you to use. Because since it doesn't dissociate completely, you have to use the K value that looks at the natural equilibrium between the reactants and the products. Now, question 9 is interesting. I was going to say it's fun, but Sarah just said it's not fun, so apparently I can't say it's fun. Okay, Erica, you did it exactly right. You did it exactly right. So you come to this equation, you're like, ooh, I'm looking at a buffer, I'm going to use this equation. And then you look at this thing, okay, I've got volume, I have the pH, interesting. I can use the pH to get back to the H plus here. And I have nothing else. I have no Ka value. I have no concentration of my acid. I have no concentration of my base. I can't calculate anything if I have 3 variables and 1 known, right? I'd have to give you 3 knowns and 1 variable to calculate that. So you could say, wow, this is a messed up problem. She obviously left some information out, but actually that was the point of the problem. The point of the problem is not to calculate the answer. The point of the problem is to remember, what does a buffer do? Like conceptually, what is a buffer good for? Right? Do you guys remember what buffers do? The whole point of a buffer? Yeah, the buffer is going to decrease pH change. So if I add in a strong acid, it's going to be like, whoa, Natalie, don't be so acidic. And it's going to react that with its conjugate base, and it's going to turn it into a weak acid, and the whole thing is going to get a little more acidic. I mean, it can't not because you just added a strong acid, but it just gets a little more acidic and not like a lot more acidic, right? And it's the same thing if you add a really strong base, as in this case. It's like, holy cow, all right, don't get your panties in a twist. We're going to get a little bit more basic, but there's no way we're going to let you get a lot more basic because then we would die, right? This is what your blood and your cell cytosol does, because your blood and cell cytosol are well buffered, because if they weren't, then all of your proteins would be denatured and you would die. So so conceptually you look at this, and you know you have to look at it conceptually because you can't use the equation, you don't have the information. That's just what you have to do. So you say, I'm adding a tiny bit of a very strong base. So I predict that the whole thing's going to get a little bit more basic. So of all the options here, if I start at 5.5, to get a little bit more basic, the pH goes up a little bit, right? Because up is more basic and down is more acidic. If I had added a little bit of a strong acid, then you would predict it would be 5.2, right? But you don't say, whoa, a whole bunch of a strong base, it's going to be 14, because that's a basic, right? Because it's buffered. Does that make sense? It's tricky a little bit, because you start out thinking you're going to use this equation, and then you realize that you can't. But then you just have to kind of apply, again, a conceptual, what do buffers do? What can I expect? What do you guys think? Okay on that one? Okay, question 10. here we've got an option to calculate. Okay, so in fact it tells you this time you're going to need to calculate. And they want to know the pH, and they tell you it's a buffer, so you know you're using this equation. And they give you a certain amount of HClO and a certain amount of ClO minus, and they give you the Ka. So awesome. I can use the Ka. One of those is the HA, one of those is the A minus, and once I solve for the H plus, I can plug it in to find the pH. I got this. All right, or I should say you guys got this. So if we do this, then my H plus is equal to the K sub A, which was 3.0 times 10 to the negative 8. Okay, and then I do have to figure out which of these is the HA and which of these is the A minus. So you guys tell me, how do you know which is the HA, which is the A minus? Perfect. This is the HA because it has an extra H, right? It's the acid. And this is the A minus because it doesn't have the H and it's got a negative charge, right? Or it has one less H and it has one lower charge, right? Okay, so that's how you're gonna kind of remember that. So we've got 0.015 molar on top. And we have, oh, where was it go? Okay, 0.025 molar on the bottom. Yes, okay. So we're just gonna plug this in. And Sarah's got the answer, but we're gonna verify because we're scientists. Okay, 0.015 divided by 0.025 times 3 times 10 to the negative 8th gives me an H plus concentration of 0.000 something 18. By the way, some of your calculators might do this. There's actually only so much space. You might end up with an answer. If you end up with an answer that says like 0.00002 with nothing else, you should be a little bit skeptical and wonder if maybe your calculator is kind of cutting it off. In this case, it really is 18, but there's not kind of a guarantee. So you can change, if you can change it to exponent, do that. You should probably learn how to do that on your calculator. But if you can't, then another option is just like count this and say, okay, it's like 1.8 times 10 to the negative 8th, and then multiply it by like 1,000 just to get it to move it over, just to make sure that there's no additional digits out there. That actually is a problem, I think, on one of the problems on this upcoming exam. So I just wanted to make sure that you guys can do that. So this is 1.8 times 10, 10 raised to the negative 8, right? Okay, so sorry, divide that by 1,000. Get us back there. All right, so that's the H plus, and then to convert that to the pH, you're just gonna take the minus log of that thing, right? So take the log of that, a minus of that, and that gives me a pH of 7.74. How do you guys feel about that one? All right, well, that's the first 10 questions. That's chapter 10. And then I think the next 10 questions is chapter 11. Again, it's a shorter exam because it's only on 2 chapters and because some of these problems take a long time to solve with the math. So I'm giving you the time so that the average student should be able to be done within an hour. Okay, so question 11, what is the best description of an alpha particle? Good, charge +2, mass of 4, and it's going to be low penetrating power because it's so massive, relatively speaking, right? So just memorizing what each of these particles are is how you'll answer this type of question. If I asked, which is the best description of a beta particle, you would say, okay, beta particle is an electron, so it would have a charge of -1, mass of 0, and then maybe like a medium penetrating power. Which of these is the best description of a gamma ray or of gamma radiation? Good, it's the 0 and 0 with high penetrating power, right? So any one of those is a fair game question I could ask. Okay, nucleon, a little bit of vocabulary. You guys got it, perfect. Protons and neutrons. It's the stuff that's in the nucleus. Those are nucleons. So perfect. All right. Here we go. Half-life. Iodine has a half-life of 8 days. If you originally have a 658 gram sample, how much will remain after 32 days? Now, I told you I wasn't going to give you these equations, so you've got to know that the amount remaining divided by the original amount, that's the fraction, right? That's equal to the fraction that remains. And that's equal to 1/2, right? Raised to the number of half-lives. Do you guys remember that? Okay. So Sarah's got it right. If one half-life is 8 days, say 1 half-life equals 8 days. My fingers are dyslexic. And we have 32 days have passed. Here we go. We're gonna say 1 half-life, 8 days. Then you can see 32 divided by 8 means that we've had 4 half-lives passed, right? So 1/2 raised to the 4, this is the fraction that is remaining. You can say 1/2, that's x. We're gonna raise that to the 4, that's y. Again, your calculator's probably gonna be something different. You could use x to the y, or the caret button is always kind of a nice one, but 1/2 raised to the 4, that's 0.0625 is the fraction that's remaining. Okay, so in this case, okay. And the original amount was 658 grams, so this one right here, that was 658. So multiply that by 0.0625, that should give me the original, that should give you the amount that remains. So multiply that by 658 and I get 41.1. Now another way to do this is just to say, look, if I know there's 4 half-lives and I have 658 grams, just divide by 2. So that's after 1 half-life. Divide by 2, that's after 2 half-lives. Divide by 2, that's after 3 half-lives. Divide by 2, that's after 4 half-lives. Does that make sense? So same process. Perfect. Okay. All right, which reaction is an example of a chain reaction? The third answer. Why is this the right answer? What is a chain reaction? Sarah's exactly right, right? So to get this reaction going, a neutron bumps into uranium, right? And of course, if you've got one uranium atom sitting around, you've got a whole bunch of uranium atoms. But in the process of breaking down, this creates 3 more neutrons, which can bump into the other uranium atoms sitting around, right? And so that gets this point where the first one splits and it makes 3 neutrons, which each strike additional, the first one comes and makes it split into 3, which could make it split in, each of those split into 3, which could make each of those split into 3, and so on and so forth. And that reaction is going to run away from you very quickly. Good. Number 15. Which particle is the one which has a relative mass of 0 and a charge of +1? That is the positron. Good. If I'd said mass of 1 and a charge of +1, what would the answer be? Proton. Good. If I'd said a mass of 1 and a charge of 0, what would the answer be? Neutron. Oh, you guys are on it. Good. Good, good, good. All right. Number 16. This one's kind of fun. I thought I pulled this out of your homework. You guys can tell me if you saw one like this on your homework. But it's kind of fun because you've got a multiple decay series. Now, you don't have to do each step individually, right? you can just do them all in a group. But we've got 232, 90, thorium. So when I say you don't have to do each individually, that means you don't have to do an alpha and then an alpha and then a beta and then a beta. You know, you don't have to do that. You just have to say, okay, in the end, I'm going to have 6 alphas. 4, 2, HE, 6 of those. And I'm going to have 4 beta decays. Okay, so that's a beta is a 0, -1. Right. All right. Excellent. And so after 6 alphas and 4 betas, what else do I get? The final stable isotope. This is the one that stops the decay process. And it's just the same kind of game that we were playing previously, right? Where we say we've got 232 on the left-hand side, and that has got to equal, here I've got 6 times 4, plus here I've got 4 times 0, which is 0, right? And 6 times 4 is 24. So 232 minus the 24 gives me 208. So the last thing here has got to have a mass of 208. Okay. And then, and if you make a mistake, don't feel too bad. Honestly, I actually ran this in office hours with another student yesterday, and I like counted this as 4 times 1. I was like, oh, I'm so dumb. Why would you do that, right? These are the kind of silly mistakes on this section that make you feel so frustrated because you're like, I know this, right? Okay, and here I've got 6 times 2, and here I've got 4 times a -1. All right, so 90 equals 6 times 2 is 12, right? So subtract 12, and then 4 times -1 is a -4. So I have to add 4 to that to get, what I'm gonna get here is 82. And it'll never hurt to just double check and say, okay, 6 times 2 plus 4 times -1 plus 82, and verify that that does indeed equal 90, just to like super double check yourself. And then you look on your periodic table, which you have printed out for your test, I hope, and you find the element with a mass of 208, actually it doesn't matter what the mass is, the element with 82 protons is lead. 208, lead 208. There it is. Does that make sense? That one's kind of fun. Give me a challenge. Okay. Next, what particle is used in this reaction to bombard nitrogen-14 and force it to decay into carbon-14? The nice thing about this one is that they've just got it all written out, right? When I describe it, then you have to come up with it all yourself, and that it's possible to, well, that is not helpful. Possible to get it wrong. So it's helpful when I give it to you here. So 14, 7, nitrogen plus something gives me, we've got 14, 6 carbon. And it looks like I lose a hydrogen. Okay. All right, so I'm just gonna do my math here and say 14 plus what is equal to 14 plus 1. Okay, so this has got to be a 1. That makes sense. Okay, and then on the bottom, I've got to have 7 plus what is equal to 6 plus 1. So 6 plus 1 is 7. So I've got to have 0 here. And so my thing, as you guys have already noted, my species with a mass of 1 but no charge is by definition a neutron. So that's what I'm going to select. Make sense? Perfect. Okay, question 18. Same thing, just predict the other product formed. And I have here polonium-210. Right, and that goes to form 4,2-He. This looks like a spontaneous alpha decay. So what else is formed? And you're going to say, okay, well, 84 is equal to 2 plus, it's got to be 82, right? And at the top here, 210 is equal to 4 plus 206. You can almost eyeball these, but I still don't recommend that you do because you have time. And if you eyeball them, there's still like a good chance that you'll have problems, right? That you'll make a silly mistake somewhere. And we don't want to make silly mistakes. We want to get them all exactly right. So slow and steady, careful and precise is the goal. Okay. Thorium-234 undergoes spontaneous beta emission. So again, he's used words here. I've used words here, I should say. 234 thorium, and now you've got to look up on the periodic table. How many protons does thorium have? It's got 90 to start with. Okay, thank you, Erica. So you have to look that up on the periodic table to answer this question. Spontaneous beta emission. Got to remember that the beta particle is in the product and that it has a charge of -1 and a mass of 0. So there's your beta particle. And what else is made? And then we can say, okay, 90 is equal to -1 plus, it's got to be 91, right? And then 234 is equal to 0 plus 234. So 234, 91, element 91 is what is that, protactinium? I think, Pa. Questions on that one? Okay. All right, then here's our last one. How many neutrons are going to be produced here? Okay, all right. Make us calculate it. So 246.96 for curium. I'll try this. 12. 6 for my carbon. 254.102. That's cool. This looks like a fission. No, a fusion, right? You're making something bigger. And a certain number of neutrons. Okay. So this is curium plus carbon goes to form, nobelium, named after Nobel, plus a neutron. Okay. And then we do our math. Okay. So I'm just going to do the top line because as it turns out, this is going to contribute nothing to the charges, so it's kind of invisible. I should say, miss this piece bit. Plus, okay. And we're solving for the number that goes in front of here, right? X neutrons. How many neutrons are formed? Okay, so 246 plus 12 is going to be 256, 258. So 258 is equal to 254 plus, it's got to be 4. So since each of those is 1, then 4 times 1 is going to make that math work out. And I just did that in my head, which is good practice, keeping my brain sharp, but I'm still going to check it because I'm on a test and I'm a little bit paranoid. Okay. 254. Okay, yeah, it's 4. So it's going to be 4 neutrons. And that's it. Any questions on that one? See how we did. Yay, we got them all right. Okay. Any questions on the test in particular before I send you on your way? And if there's no other questions, I will let you go and say good luck on the test, guys. You can do this.